Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in class 12th physics playlist in chapter electromagnetism we will study Lorentz force formula on moving charge and understand how a moving charge experience a resultant force in simultaneous presence of electric field and magnetic field, and we'll also learn how velocity selector works to select all charge particle moving with the same velocity for a certain application, and we'll also solve some exam centric numerical problem on this subject. So let's start Lorentz force on moving charge. The resultant force on a moving charge by the simultaneous presence of electric field and magnetic field is called as Lorentz force, and Lorentz force on a moving charge is basically vector summation of electric force by the presence of electric field on charge and magnetic force exerted on moving charge placed in magnetic field. For a positive charge, whether it is stationary or moving, the amount of electric force in the presence of electric field is directly proportional to strength of electric field and is equal to charge multiplied by strength of electric field, and the direction of electric force for positive charge is in the direction of electric field, whereas magnetic force on moving charge by the presence of uniform magnetic field is given as charge multiplied by vector product of velocity vector and magnetic field flux density vector, and the direction of this magnetic force is perpendicular to the plane which contain velocity vector and magnetic field vector, and this direction of magnetic force can be obtained either by right hand corkscrew rule or Fleming's left hand rule. For a moving positive charge, velocity and magnetic field both act in this VB plane, which is highlighted with yellow color, and if electric field act normal to this velocity and magnetic field plane, then for this positive charge, the direction of electric force on this positive charge is in the direction of electric field intensity, and the magnitude of electric force is QE, whereas the direction of magnetic force is perpendicular to VB plane, and that can be given by either corkscrew rule or Fleming's left hand rule. And if this brown is magnetic field flux density and red is velocity of positive charge particle, then as per right hand corkscrew rule, if screw is rotated from velocity to magnetic field in anti-clockwise direction, screw will move upward and magnetic force is in the direction of electric force. And if this red one is magnetic field flux density, and if we rotate screw in cork from velocity to magnetic field flux density in clockwise direction, the screw will move in downward direction, and in that case magnetic force become opposite to direction of electric force. So when electric field act normal to VB plane, the two force, electric force and magnetic force, may be in the same direction or they may be in opposite direction. That depends upon orientation of velocity and magnetic field flux density vectors. There is a special condition of Lorentz force relation of interest when velocity of moving positive charge particle, the direction of magnetic field flux density and electric field, all three are mutually perpendicular to each other, and position of velocity vector and magnetic field flux density vector in VB plane is such that the direction of magnetic force comes opposite to direction of electric force in the direction of electric field, and the two force, electric force in the direction of electric field and magnetic force perpendicular to VB plane and opposite to electric field intensity, are equal and opposite, and in that case the net force on this moving charge becomes zero, and without acceleration such particle moves with uniform linear velocity, and we have to study that conditions in detail. As this charge particle is moving with linear constant velocity, it means resultant acceleration or force on this charge particle is zero, or in other words we can say that force of electric field and force of magnetic field acts in opposite direction and are equal in magnitude, so that resultant force becomes zero and particle without any acceleration or deceleration moves with constant uniform velocity in a linear straight motion, and it means electric force in the direction of electric field equal to Q times the strength strength of electric field intensity, and magnetic force perpendicular to VB plane given as charge multiplied by vector product of velocity and magnetic field flux density. Both are equal in magnitude and opposite in direction. This negative sign indicates the opposite direction of magnetic force from electric force, as it is clear also from this diagram. And this relation clearly indicates the two sides of this equation, left and right, both influenced by charge amount in a similar manner. That means if we double the amount of charge, both electric force and magnetic force will get doubled. Or if we reverse polarity of charge particle, both electric force and magnetic force will reverse their direction, but again the both remain in opposite direction. So this relation is independent of charge magnitude or polarity, and it relates the strength of electric field intensity with magnetic field flux density with velocity of charge particle, and the relation is electric field is negation of vector product of velocity vector and magnetic field flux density vector. It means the magnitude of electric field intensity is equal to magnitude of cross product of velocity and magnetic field flux density, and the direction of electric field is opposite to the direction of resultant direction of vector product of velocity and magnetic field flux density. And if velocity and magnetic field got a 90-degree mutual angle, then this cross product, magnitude of first velocity vector, magnitude of second flux density vector, and sine of the angle between the two, 90 degrees, sine 90 will become 1, and the magnitude of electric field intensity in this specific case become equal to product of velocity and magnetic field flux density. And this relation E is equal to VB is a very handy, useful, friendly relation to relate dimensions of electric field intensity and magnetic field flux density. Velocity selector is a typical application which select moving charge particle of a specified velocity irrespective of mass or charge polarity or charge amount of those particles. In fact, velocity selector has a simultaneous presence of both electric field and magnetic field in a certain region, and these two, electric field and magnetic field, are perpendicular to each other, and both these fields, electric field and magnetic field, are also perpendicular to the initial velocity of charge particle that are passing through this region. So in velocity selector region, two charge parallel plate, positive and negative, produce a uniform electric field from positive to negative in upward direction as shown in this diagram, and some solenoid coil produce uniform magnetic field in this region perpendicular to the direction of electric field, perpendicular to this yellow highlighted velocity selector region towards us, denoted by dot here, and the initial velocity of particle is also perpendicular to both electric field as well as magnetic field as shown by this blue arrow. Now this charged particle will experience force by electric field in the direction of electric field in upward direction, and the magnitude of electric field force is given as Q times strength of electric field intensity, whereas the direction of magnetic force by magnetic field flux density is given by Fleming's left hand rule. When thumb, forefinger and middle finger of left hand are stretched mutually perpendicular, and this forefinger, the directional finger, indicate the direction of magnetic field perpendicular to this yellow highlighted region towards us, and this middle finger indicate velocity vector direction of moving charge. Then this thumb indicate the direction of force in downward direction by magenta arrow opposite to the direction of electric force in the direction of electric field. When velocity direction is perpendicular to magnetic field, the angle theta between velocity and magnetic field become 90 and sine 90 become maximum 1, and magnetic force become maximum QVB, and this maximum amount of force remain maximum as long as velocity remain perpendicular to magnetic field direction. So on this charge particle, the electric force doesn't depend upon velocity of charge particle, is in the direction of electric field intensity shown by this blue arrow, and magnetic force depends upon velocity of charge particle, acts in downward direction shown by magenta arrow. The idea of this velocity selector is to produce two, electric force on charge particle and magnetic force on moving charge particle equal and opposite in direction, so that the resultant force on some specified particle become zero, so that the net force by simultaneous presence of electric field intensity and magnetic field flux density becomes zero, and particle of that particular condition will pass through the region without change of their velocity direction or magnitude of velocity, and they will go straight with uniform linear velocity as shown by this red arrow direction. So for undeflected motion of charged particle along this red line, the electric force in the direction of electric field intensity QE must become equal and opposite to magnitude of magnetic force by magnetic field flux density in magenta arrow direction QVB, and with this condition the velocity of those undeflected charged particle going straight is given as a ratio of strength of electric field intensity and magnetic field flux density. Since the magnetic field force QVB depends upon velocity magnitude of moving particle, so those particle having velocity less than this ratio of electric field intensity to flux density will have lesser amount of magnetic force and higher amount of electric force, so they will deviate from their straight path in the direction of electric force or in the direction of electric field as shown by this black direction, whereas those particles having velocity more than this ratio of electric field intensity to magnetic flux density will have higher amount of magnetic force, and as magnetic force become more than electric force, then particle will deviate in the direction of magnetic force as shown by this green curvature, and those particles having velocity equal to the ratio of electric field intensity to flux density would have the same amount of electric force and magnetic force, and two forces are opposite in direction, so they without net force, without any acceleration, will go straight with constant uniform velocity in a linear straight direction and pass through this selector position, and all other particles having different velocity will get obstructed by these shields. So any charged particle traveling faster or slower than this specified velocity will be deflected either in one way or another way and get stopped here in this region, and particle of specified velocity given by this relation will go straight and get selected as a fine beam. Now this working of velocity selector doesn't depend upon charge or mass of moving particle, as both electric force and magnetic force are independent of mass magnitude, and their dependency on charge is of identical proportionality and will affect both forces of a particular velocity particle in equal amount. So this velocity selection doesn't depend upon mass or charge of moving particle. This numerical example will explain the theory of velocity selector with great ease. In a transverse mutually perpendicular electric field and magnetic field, the strength of electric field is 1500 volts per meter and magnetic field flux density is 0.4 Tesla. One electron moves straight with constant velocity. That means on moving electron there is no net resultant force. We have to find out velocity of that particular electron moving straight without acceleration. So for straight linear motion with constant velocity or zero acceleration, a resultant force on electron is zero. That means the force by electric field and force by magnetic field. Electric force and magnetic force are equal and opposite. Electric force on electronic charge is charge multiplied by strength of electric field or intensity of electric field, and magnetic force with 90-degree angle between velocity of charged particle and magnetic field is given as EVB, where V is velocity of charged particle and B is flux density of magnetic field. Now in this relation electronic charge will get cancelled out, and the velocity of moving particle become ratio of electric field intensity and magnetic flux density. Electric field intensity is 1500 volts per meter and magnetic field flux density is 0.4 Tesla, and the ratio becomes 3750 and the unit of velocity is meter per second. This example will explain use of unit vector and mathematical rule of vector product in working of velocity selector. In the problem, it is given that a proton is moving in plus z direction with v velocity, where electric field of strength E is acting in plus x direction. We have to determine suitable value and direction of magnetic field for undeflected motion of proton. So we know that in a velocity selector, all three, electric field, velocity and magnetic field, are directed mutually perpendicular. So magnetic field is either in plus y direction or minus y direction. For an undeflected motion of proton, both electric field force and magnetic field force must neutralize each other. So that means electric force and magnetic force are equal and opposite. Now electric force on positive proton charge act in the direction of electric field, that is in plus x direction, and unit vector in plus x direction is I cap. So electric force is charge multiplied by intensity of electric field in I cap direction. So magnetic force must be in minus I cap direction, opposite to electric force, and its magnitude is given as charge multiplied by vector product of velocity vector and magnetic field flux density vector, and velocity is in plus z direction, so it is denoted by unit vector in plus z direction k cap, and we have to find out direction and magnitude of magnetic field for undeflected motion of proton. And as per our theory, this magnetic field must be perpendicular to both electric field and velocity. That means it is either in plus j direction or minus j direction. So electric force on proton charge is in plus x direction, so magnetic force must be in minus I cap direction, and it is E v cross B, and B must be either in plus j direction or minus j cap direction. And as per vector product method, the vector product of velocity vector and magnetic flux vector, if need in minus I direction, then B must be in plus j direction, as vector product of k cap with j cap is in minus I cap direction. So magnetic field is in plus y direction, and its magnitude is given by magnitude relation of electric force and magnetic force. Electric force is E charge times strength of electric field, and magnetic force with 90-degree angle between velocity and magnetic field is charge multiplied by velocity and magnetic flux density. Now this electronic charge will get cancelled out, and the flux density of magnetic field is ratio of electric field intensity to velocity, and its unit is in Tesla, if electric field is in volt per meter and velocity is in meter per second. This tricky numerical will make our understanding exam centric and crystal clear. In this numerical, it is given that in an uniform magnetic field of 0.75 Tesla, a simultaneous electrostatic field of uniform strength 9 to 10 power minus 5 volt per meter is also maintained, and the direction of electric field is normal to the direction of electric field, and a narrow beam of single species, that means all particles are identical in nature, are accelerated through 15 kV, and after that accelerating potential effect, they enter in this region perpendicular to both magnetic and electric field. Now this beam remain undeflected. We have to make a guess what type of particle the beam contain, and we have also answer why this answer is not unique. So we know it's a case of velocity selector, and when electric field, magnetic field and initial velocity of particle, all three are mutually perpendicular, and the two force of electric field and magnetic field are equal and opposite, then the particle velocity is given as ratio of electric field intensity to magnetic field flux density, and electric field intensity is 9 into 10 to power minus 5 volt per meter in velocity selector, and magnetic field flux density is 0.75 Tesla, and the ratio gives us velocity equal to 12 into 10 to power 5 meter per second. And we know that this velocity is achieved by particle after acceleration through a potential difference of 15 kV. So a charged particle accelerated by V potential difference will have this much amount of work done by electrostatic accelerating potential, and that get converted into its kinetic energy, half mv square. So for these particle, the specific charge or the ratio of charge to mass is given as velocity square divided by 2 times accelerating potential, and the velocity of those selected particle is 12 into 10 to the power 5, and when this is squared and divided by 2 times accelerating potential 50 kilovolt, we got that charge to mass ratio comes as 4.8 into 10 to the power 7 coulomb per kg, and this specific charge value is the value for deuteron, which is nothing but an isotope of hydrogen having 2 AMU mass and 1 electronic charge. Now, other combination of this charge to mass ratio may be alpha particle or doubly ionized helium atom or triple ionized lithium ion, and both doubly ionized helium and triple ionized lithium got same charge to mass ratio as that of deuteron, 1 unit electronic charge 2 times mass, or 2 unit electronic charge and 4 times mass, or 3 unit electronic charge and 6 unit mass. So our answer is not unique. This charge to mass ratio could be of deuteron, alpha or triple ionized lithium. We hope this informative, useful video has explained all important aspects of Lorentz force calculation on moving charge, and now you could also answer how velocity selector works and can handle numerical problem of velocity selector. Our other learning video of same playlist are equally useful, and you can use them in your studies and share them with your friends. And if you need our online doubt clearing classes or exam centric dedicated notes, do join membership of our Shridevi classes YouTube channel by clicking join button just beneath. Happy learning. Have a nice time. Thank you very much.